Hi guys, welcome to week 6 tutorial entitled Comforts and Health IEQ, or some people say it's IAQ. Okay, it is not a very long tutorial, it's very short, and then there is a mistake in the times that in week 6 if you click on times tutorial section, you will see that it is labeled as tutorial week 10. Okay, I didn't change this to week 6, but this is what we're going to use. So please go to times and go to week 6 tutorial, and there's a bracket that says that it is labeled as week 10. Right, so let's go there now. Welcome to our times page, air conditioning and refrigeration engineering. So let's scroll down to tutorial section and find yourself the HVAC tutorial week 6, although there it says it's labeled as tutorial 10 inside. So if you click on that, okay, and you will see there it is labeled as tutorial week 10, but it's apparently is tutorial week 6, right? This is previously done, and I think I don't bother to change it. These are the questions for week 6 tutorial, comfort and health IEQ. Alright, so down here will be the answers already available to you guys. So open this in a new tab, or for myself, I will be using this with my PDF Expert app. Okay guys, so this is my PDF Expert app, and you're looking at tutorial week 6, although it says tutorial 10. So maybe you can correct it now. Okay, let's go straight ahead to the first question. Let's not waste our time. It says here, let me change to highlighter. In an occupied space, the mean velocity is found to be 40 feet per minute, or 0.2 meter per second. The dry bulb temperature is 74 degrees Fahrenheit or 23 degrees Celsius, and the globe temperature is measured to be 78 degrees Fahrenheit and 26 degrees Celsius. It means the occupied space, have a temperature of 23 degrees Celsius, while the outside temperature is 26 degrees Celsius. So we need to calculate the operative mean temperature as discussed in the lecture note. So to do this, let me clear this out. The question that you need to use is TO and TA plus TMRT divided by 2, right? We have to find the average. And also there's a equation that TO is equal to 0.45 TA plus 0.55 TMRT. So between these two you can use any of them, right? Okay, if you go back to our notes, to calculate TMRT, you need to use this equation. TMRT to the power of 4 is equal to T globe to the power of 4, and CV bar. Okay, some people use V bar, some people use V naught, and also those in fluid mechanics, it will use Q dot, right? Q dot. So here is CV to the power of half, T globe minus T ambient. Okay, so here we will use in this example we will use T as English unit. Alright, so this is the Rankine, given this 78 plus 460 Rankine, and C will be the constant, this will be the constant, right? And this V is the speed, right? V is speed. You don't have to change it to anything. And then the difference in temperature, TG minus TA. So TMRT will be 82 degrees Fahrenheit or 27.8 degrees Celsius. Okay, so then T operative, you put it back into the equation, which is this one, and you will get this answer. What is that? T0 equals to 78 degrees Fahrenheit or 25 degrees Celsius. Okay guys, so the second question is a patient room. So it is in a hospital. It is designed for 12 people only. So A, what is the minimum amount of clean outdoor air required? So you are now going to design a room in a hospital. B, if the outdoor air ventilation was based on floor area and the patient room contained 1000 square feet, at what rate it will be required? Okay, so we will use this table, and this table given a patient room. This table is available in your notes, right? In your notes. Also, it will be given in the final exam. This table comes from ASHRAE. If you're familiar with the name, I think by this time you know what ASHRAE is. Okay, so ASHRAE says if this is a patient room, the maximum occupancy will be only 10 people per 1000 square feet. That means this room, this patient room, is designed for 12 people, and the one that is said by ASHRAE is only for 10 people per 1000 square feet, right? Outdoor air requirement, if this is a CFM or cubic feet per minute per person, it should be 25. If it's a liter per second for SI unit, it will be 13. So this is the classification given by ASHRAE. Alright, so let's go. The minimum air ventilation is 25 CFM per person, so we will use English unit. Now the equation will be V dot, that means the needed supply air inside this room is 12 people, times, because it's per person, right, times 25 CFM, equivalent to 300 CFM. So this will be the minimum amount under any circumstances, okay? For 12 people, the required air will be 300 CFM. Okay, so that's the first question, the first answer. The second one, based on the floor area. How? Based in the floor area. So just now we times with 12, this time around with 10. 10 times 25 is 250. So with the 12 people inside this section, it will not be sufficient. The supply air will not be sufficient. So the question is, how are we going to make it sufficient? It's very easy. First things first, what supplies air into the room is a fan. So the supply air fan need to be having a higher capacity, so it can help to regulate air inside a small space which is not designed for 12 people. Okay, number one, if the space is really needed for 12 people. If not, then the room must be just 10 people and the other 2 have to go somewhere else. That means the hospital need to build the second maybe patient room. Okay, they need to be moved. Now the third question is, each person in a room is assumed to be producing carbon dioxide at the average of 0.0107 cubic feet per minute, or 5 milliliter per second. And air with a CO2 concentration of 280 ppm is being supplied to the room at a rate of 6000 CFM or 2.8 meter cube per second. It is desired to keep the concentration of level CO2 in the space below 1000 ppm, right? Because this is stated by ASHRAE. Assuming complete mixing, that means air that moves into the room is assumed to have a complete mixture of all gases available on Earth, okay, including the one supplied, which is the CO2. Determine how many persons could occupy the room and not exceed the desired CO2 level at 1000 ppm. Alright, so we are going to use a dispersion equation which is available in I believe in lecture 5 part 2 in the appendixes. I think it's there. Okay, so find them. First of all, you need to know what is the number of people need to occupy the room. So it is labeled as n, small n. N, what's that? N dot, right? Which is the rate, is small n and 5 milliliter per second. Therefore, the equation from here, N dot equals to Q dot T in the bracket CS over CE, which is the algebra method, and then small n is equals to 5 milliliter per second. So small n will replace the big N, right, which is this one, and equals to Q dot T, the bracket CS minus CE, and you have to divide by 5 milliliter per second. Okay, because N dot is the rate, but we want to know what's the number of people there. Okay, so therefore 2.8 times 1000 minus 280, which is given in the question, divided by 5. So the number will be 403 person can fit inside this space comfortably, or 0.0069 meter cube per second per person. So the English unit will be N 6,000, right? 6,000 times 1000 minus 280 times 10 to the power of negative 6 divided by 0.0107, and you get around 4.04%, right? Around 14.8 CFM per person. So more or less will be this much of number. Okay, that is for question number 3. Question number 4. For a given space, it is determined that due to poor location of inlet diffusers relative to the inlet of the return air, and due to partition around each workspace, about 50% of the supply air of space is bypassed around the occupied zone. So this question is regarding a space, right? But maybe there's a cupboard there, and the air supply is very far from the people which are staying on this side of the building, right? So the air that moves through here is blocked by obstacles, so it doesn't reach these people. Okay, what fraction of the outdoor air provided for the space are effectively utilized as the circulation rate is changed from 0.4 to 0.8? So there's no way to change the cupboard, so the best way is to change the air supply. So that's the question of this number 4. Okay, this is also available in the appendix of week 5 for R 0.4 and for R 0.8, which comes from these two numbers. Yeah, okay, so the equation is given as this, right? S is supply, R is return, and S is supply. Okay, so simply just put in the equations, right, and you get 0.625 and 0.883 respectively. So that is the fraction of outdoor air provided to the space, which will effectively utilize, and it will be used in the design of your air conditioning system. Okay, so that's number 4. Last question, number 5. Carbon dioxide is being generated in an occupied space at the rate of 0.25 cubic feet per minute, or in SI unit is 0.118 liter per second. Outdoor air with a CO2 concentration of 200 ppm is being supplied to the space at the rate of 900 CFM, or 0.425 meter cube per second. Now, you might be wondering why on earth that you need to supply a CO2. It's not that you need to supply this CO2 inside a space, because you take air from outside. Technically, outdoors have CO2, so you are going to suck in the CO2 indefinitely and pump into these rooms. So based on these readings, the CO2 that is pumped into this room, its concentration is just 200 ppm. So what will the steady state concentration of CO2 in ppm if complete missing is assumed? So we will use the same equation of rate, right? N dot equals to Q dot T divided by CS over CE. Okay, and then you do a little bit of algebra, you will get this CS equals to CE plus N dot over QT. Okay, since these two can cancel, but there's a plus here. That's why equation becomes this. Okay, so we have 2 there. English unit, CS will be 478 ppm. For SI unit, it will be 478 ppm. So the answer will be the same for both SI and English unit. So the steady state of concentration of CO2 after it mixed with the one inside the room is still 478 ppm, which still does not exceed the limit given by ASHRAE, which is 1000 ppm per space. Okay guys, it's very quick for lecture for tutorial week 6 because we just have a few questions and they are very easy. Just a few equations compared to psychrometric charts, and of course the cooling loads. Okay, so I hope to see you in the meetings, and my next video will be week 7, right? So see you around. Bye.